Good evening. I hope I am audible. And I'm sharing my screen. Please confirm if you can see my screen. Am I audible? Okay, I hope that I am audible and you can see my screen. I will wait for a few minutes and let people join, and after that we can start. Okay, I think we can start. People can join in the middle. So, hello everyone, welcome to the NPTEL live session for the course Sensor Technologies, Physics, Fabrication and Circuits. So, I am Ananya. I will be the TA for this session, and let me introduce myself first. I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. In this session, I will explain some of the questions related to the topics those were covered in week 3. So this is mainly a problem solving session, so I will briefly go through the theory part. I'll not explain much. I hope that you have already studied the lectures and watched those videos and gone through the assignment questions also. So this problem solving session will help you to solve the assignment problems. Also, I want to mention that I am recording the session so that people can watch it later if they need. You can also revisit those videos if you need at any time. You can unmute yourself and ask question or write it in the chat box. I'll be in the presentation mode most of the time, so I may not be able to check the questions or whatever you write in the chat box immediately, but after each question I will check the chat box. And if you have any question that I cannot answer at this moment, then I will note it down and explain it in a doubt clearing session that we will have before exam at the end. Also, one more thing, that you can use the discussion forum, the Q&A tab in the course portal for your doubts. You can write your questions there. I have also given my email ID here, but try to use these problem solving session and Q&A tab for any clearance for doubt. So let's start the session. My screen is visible, right? I'm not getting any confirmation or any response from you. And I'm audible. For some reason my desktop notification is not working, so that is why I'm asking again. Okay, thank you. So let's start. So the topics those were covered in this week. First topic was capacitive sensors and the second topic was thermal sensor. So thermal sensor, I think this will be covered in the upcoming sessions also. Capacitive sensors were, so these sensors were discussed mostly in this week. So what are these capacitive sensors? Where the capacitance is, change in capacitance is used to measure some target analyte or target material. And this change in capacitance, this happens due to change in target material. It can be like temperature, concentration or anything. So there can be different configuration for measurement of capacitance. One very common configuration is parallel plate capacitor. and the capacitance is given by the formula you already know, epsilon naught epsilon r A by D. Okay, so epsilon naught is permittivity of free space, epsilon r is the dielectric constant or relative permittivity of the material in between the parallel plates, A is the cross sectional area and B is the distance between the plates. Okay. Now here change in relative permittivity, so this is epsilon naught is constant, permittivity of free space, you know the value 8.85 into 10 to the power minus 12 farad per meter. So this is constant. Due to some change in the property of the target material, epsilon r can be changed. This is relative permittivity, or the cross sectional area can be changed, or the distance between the parallel plates can be changed. Okay, now we can measure this change by measuring the change in capacitance, and it can be measured with an electrical system very easily, the change in capacitance, and that can be converted to equivalent change in target analyte or target material or the target property, whatever we are trying to measure. So this is the basic of the capacitive sensors. Thermal sensors, so this topic was briefly discussed in this week. Basically the dynamic property or steady state property of a thermal sensor was discussed. So you know that the temperature can be sensed with a material, say a resistive material, because resistance of any material changes with temperature, and we can measure the change in resistance, and that change in resistance can be converted to equivalent change in temperature. So this is one way to design a thermal sensor. The main topic that was discussed here, that in thermal sensor what we want, suppose we are measuring the temperature of an object, say this is the temperature of an object, and we want the temperature of the object should be same as, actually the temperature of the sensor should be same as the temperature of the object that we are measuring. Okay. Suppose you are measuring temperature of a human being, so you want the sensor to give accurate temperature. You are measuring it for some medical purpose, but ideally we want this condition, but practically we cannot achieve this condition, like the object of the sensor is not exactly as object of the sensor is not exactly equal to the temperature of the object. This we cannot achieve practically, like very precisely exactly equal, but we try to minimize these errors. And how we can achieve the temperature of the sensor approximately equal to temperature of the object, that was discussed in the lecture video, so I will not explain it again. I think you have already studied those. So let's go to the questions. Before that, if you have any question, you can ask. Okay, if there is no question, I will start. This is the first question. Explain the advantages and drawbacks of a capacitive sensor. So I will wait again for 1 or 2 minutes so that you can answer in the chat box. Think about it, and you will be able able to figure out what are the advantages and disadvantages of a capacitive sensor. I will give some answers. Your answers may be different from mine, but there is no unique answers for this question. Maybe you can write in bullet points. Advantages and disadvantages of a capacitive sensor. So if I'm not getting any answers, so I will give you few points. First, let me give some advantages. Now many of these advantages and disadvantages we compare with resistive sensors. Why resistive sensors? Resistive sensors are very simple. We can easily measure the change in resistance using an electrical circuit, and as you know that most of the sensors are electronic in nature, so in those sensors mainly change in resistance is measured. It can be measured very easily. So compared to resistive sensors, what is one advantage of capacitive sensor is that capacitive sensor is less sensitive to change in temperature or temperature variation. So if you are designing a sensor, typically you want it to operate in different environmental conditions, say ranging from temperatures -5 degrees Celsius to say 50 degrees Celsius, so different environmental conditions, and you don't want the behavior of the sensor, the calibration of curve of the sensor, input output relation of the sensor will not vary depending on the environment temperature. Now in resistive sensors, whatever the material you use, like materials are sensitive to resistance change, like the resistance of a material changes depending on the type of the material. It will change based on temperature. Compared to that, capacitive sensors are less sensitive to temperature variation. It is not like it will not change the properties, it will not change the capacitance as per temperature variation, but the variation is less compared to resistive sensor. So that is one advantage. I will write it down. Capacitive sensors can be used for a wide temperature range. this is obviously an advantage in case the sensor is not, you are not using the sensor as a temperature sensor. Again, I am telling you that it is not like capacitive sensors will not respond to temperature change, but the change will not be that significant. And if you are using a dielectric material uh, in between the capacitors, in between the like parallel plates, say if your capacitor configuration is parallel plate capacitor, and you are using a dielectric material which is less sensitive to change in temperature, or you are using a material where the permittivity does not vary much with temperature change. Okay. Another advantage is these are highly sensitive and have broad bandwidth. Okay, I have given you two advantages. You can think about more advantages of capacitive sensors. I'll next go to the disadvantages of capacitive sensors. So what can be one disadvantage of capacitive sensors? So suppose you are using a parallel plate configuration. Here this you are applying positive voltage, negative voltage. There will be charge here and there will be charge here. So this will be negative and there will be positive charges. These are metallic plate. Now if there is another metal object or plate or any other metallic thing present, so there will be because say it is in vicinity with these plates and it is closer to these plates, so there will be accumulation of charge of opposite type and there will be additional stray capacitances. So that will actually change the response of these parallel plate capacitors. So in case there is a metal object in the vicinity of the sensor, that will change the behavior of the sensor. Now suppose you are designing the sensor to detect a metal object, then this will be useful. But if you are not designing the sensor for detection of metal object or something like that, then that stray capacitance will actually give rise to error or noise in your measurement. So I will write it in a sentence. The sensitivity in capacitive coupling may be reduced stray capacitive coupling. Straight capacitive coupling. Between electrode of the capacitive sensor and other metallic parts. So this is one problem with capacitive sensor. Another problem can be so the know the capacitance formula for parallel plate capacitor is epsilon naught epsilon r a by d. Now this epsilon r depends on the material between these parallel plate capacitors. Now say due to some change like dust, moisture, humidity, because of those conditions this material between the parallel plate can be changed. That means the epsilon r will be changed, and over time your sensor performance may deteriorate due to these kind of conditions. So this is another disadvantages. Dust, moisture and other environment parameters. You can think about it, what can be other parameters. Which will basically change the dielectric constant. And it will give rise to error in the measurement. So what you will do in order to like reduce the error or like mitigate the disadvantage of a capacitive sensor, say you will passivate, you will encapsulate the sensor from the environment. If you are not designing the sensor to sense any change in target material, where you will actually measure the change in epsilon r. Okay, if you are going to measure change in say cross section area or change in d, then you can actually protect this capacitor arrangement using an encapsulative layer in order to like reduce error due to environmental change. And for like a capacitive coupling error, you can use like there are shields that can be designed so that other magnetic other electronic like other metallic part, other electric field does not affect the electric field between these capacitors. You can design those kind of shields. Those are like electromagnetic shields, so that you can actually measure whatever you want to measure accurately and precisely. Okay. I hope it is clear. And is there any question? Okay, yeah, simple design, many physical parameters can be measured. Parallel plate capacitor configuration is fairly simple. We have like studied it since school, so a very simple parallel plate capacitor configuration can be used to measure many things. So you are right, and you can also think about the points I have mentioned right now also. Okay? So I'll go to the next question. So the question I will write, which of the following factors would most likely cause a false reading in capacitive sensor? So it is related to the first question, that's why I have kept it here. Which of the following factors would most likely cause a false reading? False reading means error in measurement. So the options are nearby metal objects, that are not target. Next option is high humidity in the environment. Third factor is rapid change in temperature. And option D is all of the above. So what will be the answer? What can cause error in a capacitive sensor measurement? What is the answer? All? Yes. how it is all, so I will explain for others. Now, so first point is nearby metal object that are not target. So you can design your sensor, capacitive sensor, to actually detect metal object. So the metal object detection, you can design, say, a sensor to detect metal object in for security purpose, using a capacitive type sensor. How you can design it? Say this is a parallel plate configuration of a capacitive sensor, and there are negative charges here, there are positive charges here. Now if a metal object is present nearby, okay, then so there is a certain electric field distribution here. Due to this metal object, this electric field distribution will be changed, because since it is positive charge, so there will be like negative charge here, so there will be another electric field here, so that will change the overall electric field. So detection of metal object can be done using a capacitive sensor. But if your problem statement is not that, you are not detecting any metal object, then any metal object that is nearby to your capacitor, that will actually change the capacitance value or the reading, so that will give a false reading. So first point is correct. Nearby metal object can give false reading in a capacitive sensor measurement. Next is high humidity in the environment. So capacitance is epsilon naught epsilon r A by D. Epsilon r is dielectric constant. Now this may vary due to humidity. Humidity as well as due to temperature. Epsilon r may vary due to environmental conditions. Now, depending on the material of the of this dielectric medium, that variation may be significant or not. But if the change in epsilon r is high, that can also give rise to false reading in a capacitive sensor measurement. So option B and C are also correct. So the correct answer is D, all of the above. I hope it is clear. Let's go to the next question. For a parallel plate capacitive sensor, capacitive sensors can be of different type based on the configuration. Okay, so this question is for parallel plate capacitive sensor. If it's dielectric material, has permittivity epsilon, is a function of temperature. And how it is a function of temperature, it is inversely proportional. So a parallel plate capacitor where the dielectric constant is inversely proportional to temperature with proportionality constant K. The question is, find the sensitivity of the sensor. The options are 2 pi K A by D, 1 by T square. Option B is minus Ka by D, 1 by T square. Option C is 2 pi K A by D, 1 by T. Option D is Ka D by 1 by T square. So what is the answer? I am giving a few minutes to calculate and write answer. One hint I am giving here, the permittivity epsilon is given as a function, not epsilon r. So you can see in the options also there is no mention of epsilon naught. So the permittivity is in the as a function of temperature. As a whole it is given. No answer. Here the material property is sensitive to change in temperature. So this is a temperature sensor. So what will be the formula that we will be used to calculate sensitivity of the sensor? The sensitivity will be change in capacitance due to change in temperature. So that's what you have to calculate. option C. So let me calculate also, then I will be able to answer. So what is given here? First thing is that permittivity epsilon is a function of temperature and it is inversely proportional. So epsilon is inversely proportional to T and the proportionality constant is given as K. So epsilon is equal to K by T. Okay, this is given. Now we have to calculate the sensitivity of the sensor. Now since the sensor is sensitive to change in temperature, so that permittivity is a function of temperature, that means capacitance will also be a function of temperature. Capacitance is epsilon A by D. Okay, epsilon is a function of temperature, capacitance is also a function of temperature. So we can measure the change in capacitance due to change in temperature. So our target is temperature. So how we can write? C is equal to K by T into A by D. Right? Now to find sensitivity, how we will find sensitivity? Sensitivity will be change in capacitance due to change in temperature. So from expression we will calculate it like this: dC by dt. Simple differentiation of this expression. K is constant, A is constant, D is constant. For this case we are not changing the cross sectional area and the distance between the parallel plate. So Ka by D is constant. Differentiation of 1 by T will be minus 1 by T square. Okay. So the answer is minus Ka by D 1 by T square. So this is the answer. So the answer is option B. Okay. I hope it is clear. In the question it is not explicitly given that this is a temperature sensor, but as it is given that it is a function of temperature, to calculate sensitivity we will do the dC by dt. Hope it is clear. Option D, expression wise it is same, but I think you forgot the minus sign here. Let's go to the next question. So this is question 4. Now in one of your assignment question, another capacitance configuration is given, that is coaxial capacitor. So we are familiar with parallel plate capacitors. This question is on coaxial capacitive sensor. Okay. So this is the coaxial capacitive sensor. So you can see this is the outer ring and this is the inner ring. Looks like a coaxial cable, and I think you have studied in microwave course or any similar electromagnetic course. So this is the configuration of a coaxial capacitor. There is one inner layer and one outer ring. Okay? And the voltage is applied between these two like rods or the material that is being used for this capacitive sensor. So question is, a coaxial capacitive sensor is immersed in a container of height 100 centimeter is equal to 1 meter. The ratio of outer and inner radius is RB by RA is equal to 2. When a constant DC source of 10 volt is applied as shown in the figure, so 10 volt will be applied between these two. Okay. A constant current of 6.5 nanoampere flows through the external circuit. Okay, the current is constant 6.5 nanoampere and the voltage source is also constant 10 volt. Find the speed with which the water level is rising. Assume the external circuit has zero resistance. That means whatever the applied voltage is actually it is dropped across this capacitor, okay, capacitive edge. Okay. As a hint, the capacitance of a coaxial capacitor is given. This is the expression 2 pi epsilon naught epsilon r into L by ln of Rb by Ra. These are the options for this question. And another information that is given, the relative permittivity of water is 80. So epsilon r for water. And the permittivity of free space is 8.85 into 10 to the power minus 12 farad per meter, that is written in NKC. So this is epsilon. Now I'm not asking you directly what is the answer for this question, but can you please tell me what are the steps you will follow to get to the answer? So what would be the first step? How you want to solve this problem? I hope the question is clear. Okay. It is a coaxial capacitive sensor and it is to be used for water level sensing. That is the purpose. We are applying a constant DC voltage of 10 volt and it is giving a constant current of 6.5 nanoampere. Getting the final answer is also important, but knowing the right steps are important. So if you look at these coaxial capacitive sensor, this is a coaxial capacitor. In the lecture, I think you remember a parallel plate capacitor configuration where a voltage is applied and the dielectric material between these plates, in one side it was epsilon 1 and one side it is epsilon 2. So it is something similar to this. Okay, so we will use similar approach. The overall capacitance will be combination of two different capacitors, one of which uses a dielectric medium as air and another one as water, and the value of those capacitors, two capacitors, that will depend on these length water, like the height of the water and height of the cylinder. Okay, so let's solve this. First, let me tell you the capacitance in a coaxial structure. Okay. So a coaxial capacitor is something like this. My diagram will not be very good, but I am giving you an idea. Just there will be an outer cylindrical layer and there will be an inner cylindrical layer. This will have some radius and the outer cylinder will have a radius. The voltage will be applied like this. Okay. This material has some permittivity and this material has some permittivity. Like this, these two may be different material or same material, and the overall length is L. Now the capacitance of these configuration, these two are like instead of a parallel plates we have cylindrical kind of structure, and here the capacitance will be the expression is given 2 pi epsilon naught epsilon r, whatever the medium between these two, ln of Rb by Ra, outer diameter, outer radius by inner radius. Okay. Rb is now in this case this is the configuration, and instead of a single dielectric material there are two dielectric materials with different dielectric constant epsilon 1 and epsilon 2. Let's consider this length of the water level is L1 and this is L2. Now how we will solve this question? We want to measure how the water level is rising, how L1 is changing. Now when water level will change, the capacitance of this capacitive configuration will change. So we should measure the change in capacitance. How we will solve this? We know that charge Q is equal to C into V. Okay, this is okay. Charge is equal to capacitance into voltage. Okay, and we also know that why I am relating voltage and capacitance, and I will relate current also, because these are the information given in the question. We are applying 10 volt DC, a constant current of 6.5 nanoampere is flowing. So I am trying to correlate this equation and find a relation where I can actually find the change in water level del 1, like how L1 is changing. So we know that current I is equal to dq by dt. Okay, excuse me. Current is equal to change in charge by change in time. So this expression is familiar to you. So current I is equal to dq by dt. So from q we can use this expression. Q is equal to C into V. So differentiation will be C and V. There are two variables. So we will write it like this: C dV by dt plus V dC by dt. Okay. So this expression is clear. I hope it is clear. Now what is given in the question? A constant DC source of 10 volt is applied. That means voltage V, which is equal to 10 volt, that is not changing. So dV by dt is equal to 0. Okay, at constant DC voltage, and the voltage is 10 volt, our I will be equal to, this will go to 0, this will be 10 volt into dC by dt. Okay, and I is given as, I is also constant, a constant current of 6.5 nanoampere is flowing for a constant DC voltage of 10 volt. Okay, so this is equal to 6.5 nanoampere, that is 6.5 into 10 to the power minus 9 ampere. Let me pause for a minute and tell me if you have any doubt till now. We have almost formulated our steps, like how we are going to calculate it. Here we have only, in this expression we have only one unknown, dC by dt. That we will correlate with dL1 by dt, because ultimately we want to measure how the water level is changing with respect to time. So the quantity we want to measure is dL1 by dt, change in water level with respect to time. So we can get like we can find that from dC by dt. Any question till now? No question? So what we have, 6.5 nanoampere is equal to 10 volt dC by dt. To the power minus 9, so let me write 10 to the power minus 10 by dC by dt. Place this 10 to this side. Now our capacitance is 2 pi epsilon naught ln RB by RA. Here it was epsilon RL. Now in our capacitive sensor, this total length is L1 plus L2, and epsilon is different here, epsilon 1 and epsilon 2. So our capacitance C will be this is like parallel combination epsilon ln RV by RA epsilon R of water into L1 plus epsilon air into L2. Okay. Now let's calculate this first part. 2 pi epsilon naught ln RV by RA. 2 into 3.14. Epsilon naught is relative permittivity of free space, that is 8.85 into 10 to the power minus 12. This is farad per meter, and ln of RB by RA is given as 2. Right? This epsilon naught is also given here. So this is 2. Let me calculate this. Eight point 018 into 10 to the power minus 11. I think the unit will be farad per meter. So let me not write the unit because everything is in standard unit. So in meter. So this is 8.018 into 10 to the power minus 11. Epsilon R of water is given in the question as 80. 80 into L1. Epsilon R of air is relative permittivity of air is 1. So this is 1. Right? So it is L2. And L2 we can write as 8.018 into 10 to the power minus 11 80 L1 plus, so this is 1 meter, so L2 will be 1 minus L1 if L1 is written in terms as an unit of meter, in unit of meter. Okay. So this is 1 minus L1, that will be 8.018 into 10 to the power minus 11, 79 L1 plus 1. Okay. Next, what we need to calculate, we have the capacitance expression and we have this expression like current expression. So from 2 what we will calculate, dc by dt. We will differentiate this expression with respect to t. So that will be 8.018 into 10 to the power minus 11, 79 L1 dL1 by dt. Okay, and this is plus 1, this is a constant, differentiation with respect to t will be 0. Okay, plus 0. Minus 11 into 79 dL1 by dt. Now we will use these expression here in the first from 1. So 8.018 into 10 to the power minus 11 into 79 dl1 by dt is equal to 6.5 into 10 to the power minus 10. So what will be dl1 by dt? into 10 to the power minus 10 divided by 8.018 into 10 to the power minus 11 into 79. So this will be 0.1026. What will be the unit? We are using an MKS system. Everything is in standard unit, meter, kc, and everything is in standard unit. So this unit should be unit of L1, which will be in meter, and unit of time, that is in second. So the answer is given in centimeter per second also. So few of the options. So this will be 10.26 centimeter per second. What is dl1 by dt? The rise or fall in the water level with respect to time. Okay, so that was our question. Find the speed at which the water level is rising. Speed means anything, dx by dt. So in this case speed is given by how you measure dx by dt. We differentiate the change in the distance or displacement with respect to time. Here we are measuring the change in the water level with respect to time. So that is, in our case, this will be dl1 by dt. Okay, and what we got as answer, 10.26 centimeter per second. Okay, so our answer is D. Check the solution and let me know if you don't understand any point. No question? So I hope that you will be able to solve similar numerical questions on parallel plate capacitors or coaxial cable kind of structure. So let me go to the next question. So this question is also related to the first, like the previous question. What is the sensitivity and offset of the previously mentioned sensor. For current is the output and speed of rise in the water level is the stimulus. So that is our target. We want to measure, our input is speed of rise of the water level. Which is dl1 by dt as per the expression that I have used in the previous question. So our input is dl1 by dt and what is our output? Current. So how we measure sensitivity? Delta output by delta input. Okay. So what will be the unit? Without looking at the options, what will be the unit for this case? Unit will be, our output is current, so ampere, and our input is dl1 by dt, so it is meter per second. You can also express it as in nanoampere per centimeter per second, right? So unit is and what will be the unit of offset? What is offset? If this is input, this is output, this is the say input output relation, then this is the offset. Okay. When the input is 0, right? So offset has the same unit as output. Okay, so unit of offset will be, what is output? Current. So unit of current, that is ampere or nanoampere for this case. So it is a very small current. So you can see, to measure this change in current, so in the previous question it is given as 6.5 nanoampere. So if there is a small change in this current, we should be able to measure. So one thing you should remember is that you are designing a sensor, what will be the measurement system you are using. So if it is a nanoampere current, you cannot use like a normal multimeter to measure this current, right? So you need a very specialized instrument. So these are the things you should remember while designing a sensor. This is a very small current, but it can give this kind of arrangement can give the rise of the water level, that value very precisely. Maybe that is why, maybe for this case, this kind of configuration is being used here. Okay, so the question was, what is the sensitivity and what is the option? Can you answer? I am not sure whether you have solved the previous question along with me or not, so I will directly give you the answer here. So current I is dq by dt, which is equal to d dt of c into v. So c dv by dt plus v dc by dt. Now for constant applied voltage, of 10 volt, dv by dt will be equal to 0 and current I is equal to v into dc by dt, which is for this case 6.5 nanoampere. In the question it was given, right? 6.5 nanoampere equal to 10 by dc by dt. So what we got as dc by dt, dc by dt is this expression, okay? So this is our input, right? So this is our output, and I will multiply this. Just give me a minute, I think I have made some calculations. So the output is this one. uh, so this is our input, right? So sensitivity will be input, output by input, so that will be 0.633 nanoampere per meter per second. I think this answer is not in the option, so this I guess should be 0.6337 nanoampere per meter per second. Please check the calculation again, but I have checked few times, so I think that is the answer. But the process of solving this question is like this. So output by input is equal to this value. This is basically this part is basically the sensitivity. So this is kind of output, and y equal to mx kind of relation, right? This is the sensitivity. This part. And in this expression c is equal to 0, so our offset for this is 0. So I think this is the correct answer. I hope it is clear and I am not making any calculation mistake. If I am making any calculation mistake, then please cross check it. I think I am not making any mistake, but you already got like how to solve this question. I hope it is clear. If there is any question, you can ask. Sure for which question you have answered. Oh, I think you have not multiplied this 79 part. Now you got it, right? Let's move to the next question. This question is on interdigitated electrodes as a capacitive sensor. So for an interdigitated electrode sensor with 10 electrodes, it shows 0.9 picofarad of capacitance. If the distance between two adjacent electrodes is 50 micron, the length of each electrode is 2 mm. What is the thickness of the electrodes? Epsilon r is given as 50. So there are 10 electrodes, right? These lines are, electrodes are not straight, but you got the idea, I guess. this kind of electrode structure is given, and this is a sensor. How this can be used, this arrangement can be used as a sensor. Say if one of the end of this positive or negative electrode is movable, then the overlapping area will be changed, this cross sectional area between these two plates. The we can consider these as individual parallel plate capacitor. So when one of the arm is moved, say in this side or this side, for this case the overlapping capacitance will decrease, and for this side the overlapping area will increase, so A will also increase, so that will give rise to change in capacitance, overall capacitance. Similarly, if this arm is moved up or down, then the capacitance value between these two electrodes and these two electrodes will change. Ideally, the capacitance between these two and these two are same in normal condition. If due to say in movement in this direction, say this is Z direction, due to movement in Z direction, the capacitance value between these two electrodes and these two electrodes will change. And if somehow you can measure the change in capacitance between these two electrodes, then these two capacitive configuration, then you can correlate it with the Z movement. So that is how this kind of interdigitated electrode can be used as a capacitive sensor. Now try to solve this question. I'm giving you a few minutes. The overall capacitance for an interdigited electrode kind of structure is that was discussed in the lecture notes, so you can refer to that. What will be the overall capacitance for interdigitated electrode sensor with 10 electrodes? Then from that expression, overall capacitance expression, what are the parameters given? N is given, the distance between two adjacent electrodes are given, and the length of each electrode is given. Let's consider that length of this electrode is the length for which two electrodes are overlapping, so you can use that information to calculate A. And from that overall expression you can find A, what is the from A expression of A you can find the thickness of the electrons. here the thickness of the electrodes means the width of, like thickness means this thickness. So if this is one comb and this is another comb, then this is the thickness. This is not the thickness, so the width is the thickness. I don't know how to draw it in 3D. If this is the electrode and the another electrode is brought here, then this is what we have to calculate. Actually, that is what we can calculate from the given information. So try to calculate that. No answer? So let me solve this. So for this kind of configuration, what is the total capacitance? So these are like individual parallel plate capacitor. There will be one capacitor between these two electrodes that will, so let's number this. This is the first electrode, second, 3, 4, 5, 6, 7, 8, 9, 10. So there will be one capacitance between 1 and 2, 2 and 3, and similarly there will be how many capacitances? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 electrodes, so there will be 10 minus 1, n minus 1 capacitances, or which are like parallel plate capacitor. We have to use a formula for parallel plate capacitor. So this is epsilon naught epsilon r A by D. Okay. A will be, if this is W and this is L, then A will be L into W and this gap is D. Right. So we will use this expression. Ct is equal to n minus 1 epsilon naught epsilon r A by D. Okay, so total capacitance is given in the question. It is 0.9 picofarad. So this is equal to 0.9. Pico is equal to minus 10 to the power minus 12. N is 10 electrodes, so 10 minus 1 is 9. What is epsilon naught in standard unit? 8.85 into 10 to the power minus 12. So this is in farad per meter. So this is in farad. Epsilon r is given in the question. Epsilon r is given as 50. So this is relative permittivity. So this is unitless. It's the ratio. And then A, area divided by D. What is given as D? Distance between two adjacent electrodes is 50 micron. Let's give everything in meter. 50 into 10 to the power minus 6 meter. Okay. So this farad will get cancelled. So you can find the unit from here also. This is 1 by meter square, and unit of area is meter square. Okay. So this is 0.9 into 10 to the power minus 12. This is 9 into 8.85 into 10 to the power minus 12 into 50. Area is L into W. We have to calculate W. L is given as length of each electrode is 2 mm. Into 10 to the power minus 3, right, into W. This is divided by 50 into 10 to the power minus 6. So W will be 0.9 into 10 to the power minus 12 into 50 to 10 to the power minus 6 divided by 9 into 8.85 into 10 to the power minus 12 into 50 into 2 into 10 to the power minus 3. This is 5.65 into 10 to the power minus 6. I have kept everything in meter. So this is also meter. That means W is equal to 5.65 micrometer. Let's check the options. 5.6 micrometer. So our answer is B. Okay. I hope it is clear. Let me know if there is no question. We will move to the next question. It's okay. So let's go to the next question. We don't have much time, so we'll go to the next question. The question is, for a general temperature sensor system where the heat loss to the environment is 0, okay, heat loss to the environment is 0, this point is important. If the sensor is attached to the object, how much would the temperature of the sensor, in terms of the object temperature? Temperature of the sensor in terms of the object temperature after 1 Herman time constant. You have to find the expression, and the initial temperature of the sensor is room temperature, that is 300 Kelvin. So how we will solve this? Let's first discuss bit theory here. So a temperature sensor is given. This figure was given in the lecture note also. I am referring to this. Suppose this is our object for which we are measuring the temperature, and it has a temperature of TB, say. This is like the block diagram of a sensor with an object for which we want to measure the temperature. The temperature of the sensor is Ts, temperature of the object is Tb, and T0 is the temperature of the ambient condition, the environment. Okay. What are the R1 and R2? These are thermal resistance equivalent to the electrical resistance we refer to in electronic circuits. Similar to electrical resistances. So how thermal resistances behave? If R1 is high, then the transfer of heat energy between object and sensor will be difficult. So ideally what we want, this R1 should be low, so that whatever the object temperature and sensor temperature will be same. The heat flow should be easier between the object and the sensor, and we don't want heat flow from object to from sensor to environment or sensor to object, so that the temperature of the object and the temperature of the sensor is same. So for that we want R2 to be high, ideally infinite R2 and 0 R1. Okay. Now so this is what you have studied in the lecture also. Another concept that was studied, that you must have studied, that the amount of heat transferred is proportional to the difference in temperature. Okay, so dq is equal to alpha 1 Tb minus Ts by dt. So this is pretty intuitive, like you are keeping the object and the sensor close by, and you want the temperature of the sensor to be same as temperature of the object. So if there is any temperature difference, heat will flow from one side to the other. So the change in the heat transfer, the change in heat energy will be proportional to the temperature difference between Tb and Ts, and alpha 1 is the proportionality constant that is related to the thermal resistance R1. Smaller the R1, like higher will be the alpha 1, so that the heat flow will be maximum. So it will take very less amount of time to equalize the temperature of the sensor and the temperature of the object. Now this is the heat flow. Like, heat transferred, say from object to sensor. Now the heat absorbed by the sensor will be dq is equal to mc dt. So what is m? Mass of the object or the mass of the sensor, mass of the object, because it will mass of the sensor. If the sensor material is more, it will absorb more heat. C is the specific heat capacity of the sensor material, the material that is being used for the temperature sensor. Now we have these two expressions, heat transferred and heat absorbed. Ideally, what will be, if there is no heat loss, whatever heat is being transferred from the object, that will be absorbed by the sensor. So if there is no heat loss, alpha 1 Tb minus Ts dt will be mc dTs. So this one is dt. We can rearrange it like this: dTs by Tb minus Ts alpha 1 dt by mc. And how we define thermal time constant? It is defined as mc by alpha 1. Okay. So this expression will be dTs by Tb minus Ts equal to dt by tau 1. Tau t, thermal time constant. Now this is this kind of differential equation. What will be the solution for this kind of differential equation? That will be exponential. Okay, this is 1 by t kind of expression. So if you solve, like, what will be the solution for this equation, that will be, I am directly using the expression given in the lecture note. You can go through the video how we can get here. So this is equal to temperature of the sensor is equal to Tb minus delta T exponential of minus T by tau. What is delta T here? Delta T is equal to Tb minus To, temperature of the object and temperature of the environment. That is delta T is defined as delta T. Now in the question what is given, no heat loss to the environment. So that means no heat is transferred to the environment from the object to the environment, right? And the initial temperature of the environment is 300 Kelvin, that is room temperature. So what is delta T for no heat loss to the environment? That is, environment is still at 300 Kelvin even though the object temperature is changing, say. So that means delta T, which is equal to Tb minus T naught, that is Tb minus 300 Kelvin. So this part is constant. Okay. So TS will be TB minus TB minus 300 exponential of minus T by tau T, right? From this expression system. This part is important. So you already know the expression from the lecture note, how to solve it like this. Now after one time constant, that is when T is equal to tau T, what will be the sensor temperature in terms of object temperature? Minus TB minus 300 exponential minus tau T by tau T. So this is exponential of minus 1. So this expression will be TB minus 300 exponential of minus 1 is 0.3677. So this is 1 minus 0.63 TB plus 110. So this is our sensor temperature expression for sensor temperature in terms of object temperature after one time constant. So what is the answer? 0.63, this. So what will be the expression after 5T? So that will be Ts equal to TB minus 300 exponential of minus 5. So this will be TB minus 300 exponential of minus 5 will be 0.67 6.738 into 10 to the power minus 3. So this is 0.99 TB plus 2.02. So you can see how different the expression at one time constant and at 5 time constant, right? So you now you can understand why we consider the sensor response to be stable after after 5 time constant. You can see this 2.02 is that number is very small compared to this 110, and you can realize what will be the extent of error if your sensor temperature and object temperature is in the same order, say 100 degree Celsius. What will be the error in 1 time constant and what will be the error in 5 time constant? So suppose you want to measure 100 degree Celsius, then it will be very close to 100 degree after 5t, and if it is if you measure it after one time constant, it will be a very different value. So that this way we can consider the sensor response is more or less stable after 5 time constant. I hope it is quite clear, this question. Okay. So if you have any question, you can ask. It is already time, so I will end the session here. Thank you for attending the session. I hope it was useful. Let's meet in the next week.